Okay, so kinetic energy is equal to 1/2 mass times velocity squared. EK stands for the kinetic energy, which is measured in joules. M stands for the mass of the object, which is measured in kilograms. And V stands for the speed or velocity of the object, which is measured in meters per second. So again, kinetic energy is equal to 1/2 mass times velocity squared. So we're told that the mass is 5 kilograms and we're told that the velocity is 4 meters per second. So all we do is substitute into our formula. So 1/2 times 5 times 4 squared. 4 squared is 16. So 5 times 16 is equal to 80. And 80 divided by 2, or 80 times 1/2, is equal to 40. So the final answer is 40 joules of kinetic energy. Okay, so 1b says, if the mass was accelerated from rest for a distance of 10 meters, what force was applied to it? Okay, so work is equal to force times displacement, which is equal to 1/2 m times velocity squared. M again stands for the mass. So work is the energy that it takes to move the object. So the mass was moved, and it took work to do that. So in order to find the force that was applied to it, we already know that the displacement was 10. So we just need to substitute some things. So the force times 10, which is the displacement, is equal to 1/2 times 5, which is the mass, times 4, which is the velocity, squared. So 1/2 times 5 times 4 squared is equal to 40. So force times 10 is equal to 40. Next, we divide both sides by 10. So force is equal to 4 newtons. Okay, what is the gravitational potential energy of an elevator having a mass of 500 kilograms when it is 15 meters above the bottom of its shaft? So gravitational potential energy is equal to mass times gravitational acceleration times the displacement and height. So E sub P stands for gravitational potential energy, which is measured in joules. M stands for mass, which is measured in kilograms. G stands for gravitational acceleration, which is 9.8 meters per second squared. And H stands for the change in height, which again is measured in meters. So gravitational potential energy is equal to mass times gravitational acceleration times the change in height. So now we just substitute. 500 is the mass, 9.8 is the gravitational acceleration, which is a constant, and the change in height, we're told, is that it's 15 meters above ground, so the change will be 15. Or above the bottom of its shaft, excuse me. So now we just simplify. 500 times 9.8 times 15 is equal to 73,500. So the final answer is that the gravitational potential energy of an elevator having a mass of 500 kilograms when it is 15 meters above the ground, above its shaft, is 73,500 joules. How high above street level must an 80 kilogram person be in order to have a gravitational potential energy of 70,000? We know that gravitational potential energy is equal to mass times gravitational acceleration times height. E sub P is equal to gravitational potential energy. M stands for mass, which is measured in kilograms. And again, gravitational potential energy is measured in joules. G stands for gravitational acceleration, which is 9.8 meters per second squared. H stands for the change in height, which is measured in meters. So gravitational potential energy is equal to mass times gravitational acceleration times change in height. So now we just substitute. 70,000 is equal to 80, which is the mass, 80 kilograms, which is the mass. Our constant for gravitational acceleration is 9.8, so we substitute that. So now we just solve for h. 80 times 9.8 is equal to 784. So 70,000 is equal to 784 times h. Now we divide both sides by 784. 70 divided by 784 is approximately 89.3. So a person who is 80 kilograms must be approximately 89.3 meters above street level in order to have a gravitational potential energy of 70,000 joules. A ball with the mass of 10 kilograms is dropped into a spring from a height of 1 meter above the spring. Part A says, what is the gravitational potential energy of the ball before being dropped relative to the top of the spring? Gravitational potential energy is equal to mass times gravitational acceleration times the change in height. E sub p stands for gravitational potential energy, m stands for mass, which is measured in kilograms, g stands for gravitational acceleration, which is 9.8 meters per second squared, h stands for change in height, which is measured in meters. So again, E sub p is equal to mass times gravitational acceleration times change in height. We're told that the mass of the ball is 10 kilograms. G is a constant, which is 9.8, and we're told that the difference or the displacement in height is 1 meter, so we just substitute. So 10 times 9.8 times 1 is equal to 98. So the gravitational potential energy of the ball before being dropped relative to the top of the spring is 98 joules. If the spring constant of the spring is 50 newtons per meter, what is the maximum compression experienced by the spring once the ball lands on it? PE sub spring is equal to 1/2 K times x squared. PE spring is equal to the elastic potential energy of the spring, which is measured in joules. K is the spring constant, which is measured in newtons per meter. And x is the amount of compression relative to equilibrium position. So again, elastic potential energy is equal to 1/2 times the spring constant times the amount of compression squared. We know from the last problem that the potential energy is equal to 98. So we substitute that in. We know that spring constant is 50. So now we're left to find out x. So we solve for x. 50 divided by 2 is equal to 25. Now we divide both sides by 25. So we're left with 98 divided by 25 is equal to x squared. So we take the square root of both sides. The square root of x squared is equal to x. And the square root of 98 divided by 25 is approximately 1.98. So the maximum compression experienced by the spring once the ball lands on it is approximately 1.98 meters. How fast is the ball moving just before hitting the spring? The velocity just before impact is measured as v equals the square root of 2 times gravitational acceleration times the displacement in height. So the gravitational acceleration is equal to 9.8 meters per second squared, and the height, or the change in height, again is measured in meters. So this is our formula. Velocity is equal to the square root of 2 times gravitational acceleration times change in height. We substitute. G is a constant, it's 9.8, and h is equal to 1. So we simplify. 2 times 9.8 is equal to 19.6. The square root of 19.6 is approximately 4.43. So the velocity, or the ball, the speed of the ball before it hits the spring, just before it hits the spring, is 4.43 meters per second. Okay, so for the last problem, how fast is the ball moving when the spring is at half maximum compression? So I believe that when the spring is at half maximum compression, that means that the kinetic energy, which is 1/2 mass times velocity squared, is equal to the elastic potential energy. So when the spring is at half maximum compression, it means that kinetic energy and elastic potential energy are equal to each other. So what we're asked to find is what is the velocity v. So we know that the mass is equal to 10, so we plug that in. We know that the constant is 50 newtons per meter, spring constant. We were given that in part B. And we know that the ball is moving at the square root of 98 divided by 25. So that's the maximum displacement. That's the maximum compression of the spring. So we need to know what's half of that. So we multiply 1/2 times the square root of 98 over 25, and we're going to square that. So what we substituted in for our maximum compression was 1/2 times the square root of 98 over 25. Next, we simplify. 10 divided by 2 on the left side is equal to 5. 50 divided by 2 on the right side is equal to 25. 1/2 squared is equal to 1 over 4. And the square root of 98 divided by 25 squared is equal to 98 over 25. So again, we simplify. We divide both sides by 5. The left side is v squared, and the right side is 5 times 1/4 times 98 over 25. Next, we simplify further. 5 times 98, all divided by 4 and 25 is equal to approximately 4.9, or exactly 4.9, excuse me. So now v squared is equal to 4.9. So we take the square root of both sides. V is equal to approximately 2.21 meters. So it's half the maximum velocity. So half the velocity of the ball just before hitting the spring is what it is. That's a speed. Half the maximum velocity just before it hits the spring. And that's our final answer, 2.21 meters.